Hello everyone, today we're going to be adding caves into our little procedural terrain game. So in the previous episodes we've added the procedural terrain, we've added the simulated water, and we've added trees that we can plant that grow over time, that we can chop, that drop saplings. So today I thought it'd be cool if we just covered how to use some cellular automatons to create caves. So we'll just go over those real quick. Because it's actually not that difficult. The concept is going to be pretty similar to how we did the water. We're just applying it in a slightly different manner. So to get started, what we'll want to do is open up the project without the caves, which I have over here. And we just want to come into our play game, which is our main HTML file here that has all of our logic for this. And we're going to want to add a import. So we'll just say script with a src equal to, and we'll call this cave simulation.js. And then we can close this and add in the closing script tag. I'll hit Control-Shift-I to open up the console down here, just so that we can keep an eye on it. We can then come over to the side, right-click, new file, cave simulation.js. Once that's done, we can come into our sketch. And inside of our sketch, we really only need to do a couple of things. The first thing we have to do is come into our setup function. So we'll come up to the top and we'll find the setup. So right here we have our terrain generation and then our trees. And what we can do is we can simulate our caves right here in between our terrain generation and our caves, or in between our terrain generation and our trees. That way we don't get any floating trees if the cave does come up to the ground level. The other thing we have to do is we have to find where we are generating the terrain down here. So let's come down to, I think the function we called it was paint terrain tiles. So we have it right here, paint terrain tiles. And then inside of paint terrain tiles, where we go through the different Y levels, where we have the sky, we have the grass, the dirt, and then the stone. What I'd like to do is come into the stone area. And then once we're in the stone area, I want to add a call to a seed caves, which we're just going to do right below everything else here. So the reason why we're seeding the caves like this is we're only doing it below this Y level. And then if things do bubble up, they can, but you'll have very sparse caves near the surface. So once we have this, we now need to actually create this function. Otherwise, we'll just get an error over here. So let's come into our cave simulation and let's create this function. So to do this, we're going to start with a comment, and the comment is just going to say that it seeds the caves. It'll then take in a node. And for this node, we just want to check what our cave density is. Now, the cave density is something we haven't defined yet, so we should probably go do that. Let's come over to our constants, and inside of our constants, we can come below the sapling drop rate, and we can just declare a const for the cave density. We'll set this equal to 25. The bigger your map, the more you're going to want to crank up the cave density. In very large maps, you want to go probably as high as like 50 out of 100 maybe. So for this one, we're just going to leave it at 25. And then once we have that, all we do is we check if a random number between 1 and 100 is less than our cave density. And if it is, that means we have like a 75% chance of the random number being larger. So only a 25% chance of getting a cave. But if it is, then we set the node type to be of type sky. Once this is done, we then need to create our simulate caves function, because that's also throwing an error. So let's just come up to the top real quick and let's create a empty function just so that it stops yelling at us. So we'll just call this simulate caves, and this is just the main cellular automata function to generate the caves. So we can save that. And now you can see we get a whole bunch of little air pockets down here, but they don't look nearly as organized as these do. So how did we get these to look so crisp? Well, the basic idea is you take these pockets and you apply similar rules to what we did with the water. With the water, we checked all 4 neighbors of the water to see what the neighbor's water level is. If the neighbor's water level was below our water level, we pushed a little bit of water over. And if we ran out of water, we stopped pushing water. In this case, running out of water just means if we're like, you know, this block right here, we only have like one air pocket, but we have 8 neighbors that are filled. We probably want to change this to a like stone block, right? So we want to fill this in. On the other hand, if you have something like down here where you have multiple neighbors that are all air pockets, you might want to take this one and set it to air, take this one and set it to air, take this one and set it to air. And then here you might see, okay, well, this seems mostly like it's 50-50 split, so we'll just leave this alone. And as you go through and you do this, you'll start to prune off some areas. And then each time you apply another iteration, because we'll be looping through this a couple times, we'll just start to prune it out until eventually you get a nice smooth looking cave similar to this. Of course, that's not exactly what it'll look like, but that's how you get these well-defined caves. So, okay, inside of our simulate caves function, because we're basically done in our other files now, we need to do a couple things. The first thing we need to do is create a for loop. We're just going to say for let I equals 0, I is less than cave iterations, I plus plus, and our cave iterations is another constant we have to declare. So let's come into our constants file and we'll just say cave iterations, and we'll set this equal to, I don't know, let's just say 5 for now. Or actually, let's leave it as 1. Why not? So we'll leave it as 1, and then we can come back over to our cave simulation and we can create a copy of our grid. So we store all of our nodes in a grid, so we want to create a copy of it. So we want to say let cells equal, and there's a couple ways to do this. Basically, we want to create a copy of the grid that won't change the original. So you can either do like a JSON deep copy, or I just actually learned about this. I don't know if it's supported in all browsers, but there is a function you can call that's called structured clone that does essentially the same thing as a JSON.stringify, JSON.parse. So you could also do something like cells equals JSON.stringify, and then you want to stringify your grid, and then you want to do a JSON.parse. I think that's the order you do it in. So that's another way to do the copy. Basically, you take your grid, you make it a string, then you copy your string, and then you convert it into JSON again. So the structure clone seems to do something similar, but don't quote me on that. So once we have this though, we now have a copy of our grid, and we can do our checks to see the state of our copy, and then we can apply our changes to the actual grid. The reason why we do this is just if we're updating the grid, then every time we like change this block and then we get to the next one, we then have to check what the original value of this block is, which means we'd have to store it somewhere, and this just allows us to store it like this, and then we just store a copy for each iteration. We can then go through and we can say, all right, so now we need to do a for loop through each of these cells. So we'll do that. We'll say let j equal 0, j is less than cells.length, j plus plus. Then for each of these j's, we need to count the number of neighbors that are filled, and we consider it filled if it is not a skyblock. So we'll just say let num filled neighbors equal 0. We then want to get the node that is at the jth index. So we say let node equal grid j. We then also need to get the cell that is at the jth index. Once that's done, we then want to check if the node or the cell is below ground. And the way we do this is with a function where we just check and we return a Boolean. It returns true if the thing is above ground, and it returns false if the thing is below ground. So maybe we want to change this to is above ground. And then if it is above ground, we continue. If it's below ground, we do that. So let's grab this function right here. We can come down here and we can just paste in the method signature with the comment, and then I'll rename it. So like it says right here, it returns true if the cell is above the ground level. So how do we do this? Well, the first thing we have to do is we have to convert our cell into the y level. So we grab the cells.y to get the y position of the cell, But we also have to grab the noise amount. And the way that I do this in the sketch is when we generate the terrain, we set the Perlin noise value here to be the density on the node. So we're just storing the density. Once we have that density, we can then say, all right, let's set the noise amount equal to the node's density times the Y position of that cell. This is where it gets a little bit confusing, but because this is JavaScript, 0, 0 is in the top left, which is the most convoluted thing imaginable. So we have to take the Y level and set it equal to the height of the document minus the Y position. So you can imagine if you're at the top left for 0, 0, you take height, which is like down here, minus 0, 0, so now you're at the bottom. If you're 15 down from the top, you take height minus 15, so now you're 15 up from the bottom. It's just so that we can have our terrain's bottom be at the actual bottom of the page instead of having everything upside down. It's a little bit confusing, but unfortunately that's just the nature of how this has been constructed. But then we can take the noise amount and check if it is less than the Y level. And all I'm doing with this is I'm just following the logic that our sketch has, because when it checks how it wants to paint the terrain tiles, the stone is painted right here, and it just checks if the noise amount is greater than the Y level. So in the cave simulation, we just do the opposite. Okay, so that handles our above ground function. What do we do next? Well, there's actually only 3 calls left. Unfortunately, they're a little bit misleading there, because the first one is a let neighbors, where we try to get the neighbors of the cell. So to get the neighbors of the cell, we have to create another function, which is going to require us to create a couple more functions. So we get the neighbors with this method call. We then say, all right, we need a neighbors array. We need to get the X and the Y from the cell. We then need to check for the X-min, the X-max, the Y-min, and the Y-max. Again, it's very confusing, but the basic idea here is we're just checking all of the locations around our node here. We then have to do 2 for loops. Basically, we have to go from our X-min to our X-max and our Y-min less than or equal to our Y-max. Once we have that, we then have to make sure that specifically for the situation where I is equal to X and J is equal to Y, which in this case, if you're imagining, let me just break some blocks so I have something to work with here. If you're imagining that we are checking the red block right here, I is equal to X and Y is equal, or J is equal to Y when we are on this red block. So what we want to do is just make sure that whenever we're on this center block, we're not including it in our list of neighbors so that we don't include ourselves in our list of neighbors. Once we have that, we can then grab the actual neighbor by calling a getNeighbor function. Like I said, this is a little bit deceptive because there are a couple nested functions here, but I thought this was cleaner than throwing everything into one. So let's create a getNeighbor function. It takes in a X and a Y, and then it does a little bit of logic. This is similar to our block.js function that gets the block by the X, Y, and the array. Except here we clamp by the values to make sure that we don't go off the screen on the left, off the screen on the right, off the screen up top, and off the screen on the bottom. In the cave simulation, we're not going to do that. The reason being, if we do clamp it and we only go to the edge of the screen, what can happen is you can get a whole bunch of caves that'll appear along the border of your world, and you don't want that. So, well, I mean, maybe you do, but your whole bottom of your map could just get empty and it looks a little bit strange. So what I do here instead is I check for the X and Y. I take off the modulus to get rid of the remainder so that this is an even multiple of my block size. I then divide it by my block size, so this is exactly the number of blocks. I then need to get the index because this is a one-dimensional array that represents a two-dimensional space. So I set the index equal to the Y index, which is the blocks over to the right, plus the number of blocks down times the number of times we've gone over. So this is just our offset to make sure we're in the correct position in a one-dimensional space. We then finish off by calling we get the cell inside of cells, which is just a copy of our grid. And then we do something that's a little bit strange, but we return a get neighbor from cell function that takes in the X, the Y, and the cell. So the reason why we have this function is because we have to check if it's inside of the bounds of the world. We start by checking if y is less than 0, so if it's up here, or if y is greater than or equal to the height, so if it's down here. We then have to check and see if it's less than or equal to 0 on the x, or if it's greater than or equal to the width on the right. Once we have all of that checked, if those conditions are true, so we're outside of the world, we then want to return a cell that just has a block type set to stone, so we can trick the upper algorithm into thinking that we have a block type of stone there, even though we're outside of the world. So then we return this cell. Otherwise, we come down here and we just return a cell. So this right here is a bit of a guard clause. If this condition ever evaluates to true, we just return this fake cell. Otherwise, we'll get down here and then we can return the cell that we passed in, basically. So, okay, we now have that. We can come up to the top, and up top here, we have our neighbors. We now want to count the number of filled neighbors that we have. So we call a function that is called count filled neighbors. And then we can create that just right down here, I guess. And we'll say, all right, how many filled neighbors do I have? Well, we need to start with a count set to 0. We then need to iterate through this array, which we'll just do by going from, I guess, let's change this maybe to I equals 0. I is less than neighbors.length, I plus plus. We can then grab the neighbor inside of the neighbors array by doing neighbors I. We then check, is this neighbor of type not sky? If it is of type not sky, that means it's filled in with something. So let's increment our number of filled neighbors. And then we can come down to the bottom here and we can just say return the number of filled neighbors. Excuse me. Once that's done, we can come down here to line 77, where it is a little bit upset with us for referencing cells. So we can come up to the top here if we get rid of this let. Once we've done that, we can then come back down to our getNeighbors function. So inside of our getNeighbors function, we need to actually push our neighbors in, or push our neighbor into our neighbors, and then we need to return the list of neighbors. Once we've done that, we are now back to actually seeing our grid so we can continue with what we were doing. So up here we have our number of filled neighbors. The last thing we have to do here is call a function that will update the block types based on what they are. So we'll call a function called update block types. It'll take in the node that we grabbed up here because we're actually changing the node, we're not changing the cell. And then it'll take the number of filled neighbors that we have here. This function we can just place wherever we'd like, really. We'll just put it down here, I guess, below the count filled neighbors. So again, a whole bunch of comments here, but the basic idea is we check how many filled neighbors there are. If there's more than 4, we then have to do another check for some small pockets of error to get rid of like this single block right here. If there are 4 or fewer neighbors, then we just set the node to be stone. So what does this look like? Well, we start with a if statement. If there are more than 4 neighbors, for now, let's just do nothing. And we'll say else there's not more than 4 neighbors, so let the node type be set to stone. Now you'll see nothing really changes here because this actually needs to be sky. Once we change it to sky, you'll see that the nothing really changes with the single pockets of air, but our overall structure here starts to look a lot better. If we come into our constants, we can change the number of cave iterations to 2. We can change it to 3. We can change it to 5. And then you start to see how the caves get bigger and smoother as we do that. If we change the cave density here up to, let's say 40, most of our stuff is gone. Even if we change our cave iterations down, you can see how even just one iteration with a density of 40 gets rid of roughly 40% of our stuff. So if we set this to 90, you only get like 3 or 4 blocks left. So we'll go back to our 25 here and we'll set the cave iterations to like 3, just so that we have something to work with, because this gives us a couple of pockets with these single blocks. So, okay, let's get rid of the single block problem now. So the way we do this is if we have more than 4 filled neighbors, we then call a function that fills the small gaps with stone, where we pass on the node and the number of neighbors. And this we can just place right down here, which is just once again going to take in the node and the number of neighbors. And all we do in this function is we just check if the number of filled neighbors is greater than 6. So that means you pretty much have like maybe 1 or 2 blocks next to each other that aren't filled, but everything else around it is filled. So this one right here has 1 unfilled neighbor, which is 7, which is greater than 6. And we then check if the block type is equal to sky, because we're also not trying to count it against a block like right here if it has a diamond block next to it. So we only make sure that it is counting this if it's a sky block problem. So we don't want to, we don't want to fill in like this diamond block with a stone block without this check, because then we're just getting rid of our ores for no reason. So for example, if I get rid of this and then we come in here and we set the node.block type to be equal to stone, you can see that we start to lose a lot of our ores. If we put our check back in for the sky block type, and then we set this to be stone, you can see we keep a lot of our ores all over the place. And in most cases, they'll actually stick out a bit, because they're just exposed to the air because they count as the wall, but they're not at risk of being pruned like that. But yeah, that is essentially how you can do caves inside of a procedural terrain using cellular automatons, which is pretty neat. You can, of course, change your parameters, and the bigger your map, the more you're going to want to tweak them. So here, this is a ridiculously oversized map. You'd of course want to break this up into chunks in an actual game. But if we change our number of iterations here to, let's say 5, you can sort of see what this does to the impact of the caves. It takes longer to run because it has to loop through extra times, but we can even increase the cave density if we'd like. So that might be a bit much. Maybe we want to change this to like, I don't know, 35. So there you go. You get these really skinny looking caves here, or these skinny looking pieces of land with most of the ground missing. So you would of course want to mix these up a little bit so you get a combination of everything. But it is very cool to see how simple it is to create a structure like this that you can then use to vary up what your landscape looks like beneath the ground. But yeah, that's going to do it for this video. Hopefully this was helpful, and hopefully I'll see you in the next tutorial.